So, a very good afternoon, good morning, and good evening to all. I, Dr. Pallavi Saxena, SSC member of iLEAPS, and Dr. Samina, Project Administrator of iLEAPS, welcomes you all on the occasion of iLEAPS Global Colloquium Series 2022. So iLEAPS is a global research project of Future Earth and which understands how interacting physical, chemical, and biological processes transport and transform energy and matter through the land-atmosphere interface. So just give me 1 minute. So the prime purpose of this colloquium is to introduce the scientific society people with the distinguished and significant work of eminent scientists all over the world. So it is a very bright opportunity for the early career researchers to interact with the distinguished speakers and establish the bridge between the ideas and knowledge through this platform. So our first speaker of this series is Dr. Benjamin Poulter, research scientist, GSFSC, NASA, and he is also the co-chair of iLEAPS. So Ben received his PhD from Duke University and worked at several European institutions before joining NASA in 2016. His research interest focuses on terrestrial ecosystems and how climate change and land use change affect vegetation dynamics and biogeochemistry. So he serves as he is a contributing author to the IPCC AR5 and 6 reports and to the United States 5th National Climate Assessment. So today he will deliver the talk on iLEAPS as an integrator of the Earth System Science Networks, and he will give us the insights about that how iLEAPS is interacting with the greenhouse gas emissions and to enable adaptation practices. So we have privilege to have Dr. Benjamin Poulter with us. Dr. Benjamin Poulter, over to you.
Okay. Thank you for the introduction. Can you hear me okay?
Yes.
Okay, great. Yeah, well, thanks again for the introduction. And thank you. Okay, so one second, a button just came up. Okay, you can see my screen okay?
Yes, the screen is visible.
All right, great. So yeah, and thank you for organizing the this symposium series for iLEAPS as part of what you're doing on the Science Steering Committee. I encourage everyone who's on the webinar right now. I don't see your names, but I encourage you all to join the other webinars that we'll be hosting this spring. So so again, I'm Ben Poulter. I'm currently co-chair for iLEAPS. And a research scientist at the NASA Goddard Space Flight Center in the Earth Science Division. And I wanted to take the opportunity today to sort of give a perspective on why iLEAPS exists, what some of the linkages are between the iLEAPS activities and how we're trying to understand the Earth system. And I decided to do this by reviewing some of the studies that have come out over the last year related to the COVID-19 pandemic and the impacts that it has had on human behavior and how this has fed back into changes in greenhouse gas emissions, air pollution, and atmospheric concentrations. And I think COVID-19, while it's obviously caused tremendous social and personal upheaval for everybody at this point, also has provided an opportunity for us to understand the monitoring systems that we have that are targeted toward understanding the Earth system and the way that human society interacts with the Earth system. And then to use this as an opportunity to really sort of check how well we do understand the role that humans play in the Earth system, whether the monitoring systems that we have are accurate enough, just well distributed enough, and to sort of think about that science policy interface from a new perspective. So just briefly, iLEAPS, for those of you that are not familiar, is a global research program within Future Earth. I'll discuss Future Earth further down, but Future Earth is sort of a successor to the International Geosphere Biosphere program that was established in the 1980s. And as a global research project, iLEAPS is associated with other research projects such as the Global Carbon Project, AIMS, and other groups. And within iLEAPS, our mission is to really enhance the networking opportunities of scientists across all career stages, with a particular focus on early career scientists, where the focal areas include linking scientific studies across health, biodiversity, climate, food, and food security. And to think about these in the context of the greenhouse gases that regulate Earth's climate. iLEAPS acts as a communication hub. We host several workshops, both at the regional scale, and then we have an open science conference, which is currently scheduled for this spring of 2023. And then through these workshops and networking opportunities, we've supported publications on atmospheric chemistry and land ecosystem atmosphere processes. And iLEAPS really gives an opportunity to those sort of at the earliest stages of their career to join these networks and sustain these networks going forward. And I remember as a postdoc myself, joining several of the iLEAPS workshops and really gaining from those in terms of meeting new people and being able to think about more transdisciplinary research in my own work. And then to sort of bring this back a bit more directly to what I do, I work at the NASA Goddard Spaceflight Center in the Earth Science Division, and this graphic is sort of required to be shown as a NASA scientist, and it is presenting the current operational as well as pre-operational and formulation missions that NASA is operating. And so we can go all the way back to Landsat 7, which was launched in the mid-90s, to the MODIS instrument aboard Terra and Aqua spacecraft, and so to work our way back in or so forward in time to put all of the Earth observations that NASA is making in context. And so currently I'm working quite intensely. About half my time is spent on this ESO, or the Earth System Observatory, where NASA is developing 4 new missions to make observations of our atmosphere, our land surface, where we make land surface observations through measuring the optical properties, but also the backscatter associated with ecosystem structure, and then also missions related to changes in the hydrologic mass balance. So something similar to a GRACE mission, which is measuring the gravitational anomalies of the planet, and you can link those back to water storage. So there's a lot of time that could be spent on this image. I'll just highlight a few of the opportunities that I think folks would be interested in on the call. This inner band is highlighting instruments that are located currently on the International Space Station. And so we have the JEDI instrument, which is a waveform LiDAR, providing roughly 20-meter footprints of ecosystem structure. This has been orbiting now, on orbit for about 2 years, and there are hundreds of thousands, if not millions, of data points that can be linked to ecosystem structure. There's EcoStress, which is a thermal imager measuring land surface temperature and emissivities that can be linked to water stress, water use efficiency, and to also detect active fires. There's OCO3, which is a greenhouse gas instrument making column CO2 retrievals in the shortwave infrared. And then there's sort of other missions associated with calibration and validation. So in orange here, these are missions that will be launching in the near future. EMIT will be a imaging spectrometer, so we'll be providing hyperspectral information on the land surface. And then in the outer band, we have sort of the free flyers that again include sort of the recently launched Landsat 9, but also things like ISAT, which is a photon counting LiDAR, making measurements of the ice altitudes, but can also be used to look at ecosystem structure. One of my sort of topic areas. Things like Cygnus, which is designed to have multiple applications, including measuring surface water inundation, which is important for understanding wetland dynamics. There's the free flyer, OCO2, the SMAP instrument, which is making measurements of soil moisture and freeze-thaw status, and so on. So we have an amazing portfolio of missions taking place at NASA, and so I'm happy to answer any questions on that later in the presentation. So one of the driving sort of aspects of iLEAPS is climate change and the role that humans are playing in climate change. Over the summer of 2021, the IPCC released the 6th assessment report for Working Group 1. And so these figures are taken from the summary report for policymakers, with the figure on the left simply documenting the changes in global mean surface temperature, showing that there's been about a 1.1 degree Celsius warming since the Industrial Revolution. And we know through quite specific attribution studies, as well as simply the energy balance of the Earth system, that this warming is due to human activities related to the burning of fossil fuels and also land cover change. One of sort of the other remarkable aspects of what we've learned about the Earth system is this linear relationship between the cumulative CO2 emissions and the change in surface air temperature. And so this is known as the transient response to cumulative emissions. And it simply shows that if you know the cumulative emissions of CO2 or CO2 equivalents, you can predict fairly well what the change in air temperature will be. And so today, since the Industrial Revolution, we've emitted about 2,400 gigatons of CO2. And so this relates to about a 1.1 degree Celsius warming. And so we can predict based on the shared socioeconomic pathways that are used to evaluate different idealized futures, what that means for the change in surface air temperature. And then we can also use this at different timescales to evaluate how much of the carbon budget is remaining for us to be able to avoid things like the 1.5 degrees Celsius target, or the 2 degree Celsius target that was set by the Paris Agreement in 2014. So sort of within the context of iLEAPS networking activities and climate change as one of its core areas of research, I'd like to now move on to present some of the lessons that we learned from COVID-19 and its indirect impacts on the Earth system, and then discuss this in the context of science networks and how they can help sustain further observations of the Earth system. So as we're all well aware, COVID-19 sort of was identified in December of 2019. And there was a first wave of lockdowns that radically altered human activities that began in around mid-March of 2020. And these lockdowns were intended to slow or stop the spread of the pandemic. But unfortunately, you can see that we've had waves globally since then, and we're currently in this Omicron peak. Early on in the pandemic, folks like Noah Diffenbach at Stanford University and others came up with sort of pathways of how they hypothesized COVID-19 would affect the Earth system. And so you can follow these pathways through the various arrows here, where COVID-19 would increase mortality rates or either lead to restrictions. This would have direct impacts on human health, which would then affect our food supply and our economic systems, and eventually affect the way that we interact with our natural ecosystems. And then there were sort of the pathways associated with just the simple restrictions of human activity, particularly on mobility and transportation, which is responsible for about 10% of global CO2 emissions. And then you can track these through to how the reductions in transportation emissions would affect air temperature or affect air pollution and synoptic scale meteorology. And so this is sort of the starting point, I think, for where folks thought that COVID-19 may have this imprint on the Earth system. And so early on in March, April of 2020, our air pollution spacecraft and the instruments TROPOMI and OMI fairly quickly detected improvements in air quality through a decline in nitrous oxide. And so the figure on the left shows the concentration of nitrous oxide using the TROPOMI instrument, and this is sort of prior to the lockdowns, and then in January of 2020, and then in mid-February, you can see that there's been this sort of radical improvement of air quality, but through the reductions of NOx. And the scientists here compared the expected decline from sort of a baseline of years to what actually happened in 2020, and saw that these declines in emissions were about 50% larger than what typically happens around this time of year. And NOx is a particularly interesting trace gas, given its very short lifetime in the atmosphere. So it has a lifetime on the order of hours compared to decades or hundreds of years for gases like methane and CO2. And so with NOx, you can very precisely pinpoint the source location of where the gas is being produced. On the right-hand side, you can see in the southeastern United States, so the mid-Atlantic and in states like Florida, that this was sort of the average NOx concentrations prior to 2020, and then in 2020 we see this fairly significant reduction in NOx concentrations. So later in about April, well, I guess like May, June time of 2020, studies started emerging about what the impact of COVID-19 was on CO2 emissions. And so the Global Carbon Project, led by Corinne Le Carre, developed a model that could scale historical CO2 emissions with information based on the lockdown and how it affected the different sectors producing CO2 emissions. And so they predicted in roughly June 2020 that there would be about a 7% decline in 2020 CO2 emissions. And then several other studies emerged, things like the Carbon Monitor program was established, by Julie and Lipsier, where they were taking sort of near real-time observations and sort of an Internet of Things approach to reconstruct CO2 emissions. And by the end of 2020, the reduction of CO2 emissions was closer to about 5.5%. There was sort of a lot of interest in how the recovery of CO2 emissions through the recovery of the global economy would affect the emissions in 2021. And the Global Carbon Project in the latest carbon budget has estimated that 2021 emissions will increase relative to the 2020 emissions by about 4 to 6%, which would put global CO2 emissions back within the 2019 total emission estimates. And then just this morning, there's news coming out that US emissions for 2021 increased by about 6.5% in 2021 relative to 2020. And so this puts the CO2 emissions back to the 2019 levels. And much of the rebound of CO2 emissions is coming from the transportation sector. So what did the reduction of CO2 emissions mean for CO2 concentrations? Well, we were able to carry out some studies using the CO2 greenhouse gas satellites. This is an image of the Orbiting Carbon Observatory number 2, OCO2, which takes advantage of the absorption of the CO2 gas in the thermal infrared, which is why CO2 is a greenhouse gas, and then carries out retrievals of those reflectance measurements to estimate what the column CO2 concentrations are in the atmosphere. And so this middle panel is showing that based on a modeling approach this designed, that there was a decrease in the column CO2 concentrations over parts of Asia in early March compared to what would have been expected as an increase in 2020. And then later in the year, in April, we also see this decrease in the expected column concentrations of CO2 shift over to the United States, which by then was in sort of the full lockdown mode. And and then on the panel on the right, we can compare the column CO2 anomalies for 2020 with the previous year patterns of column CO2, and you can see in the black line the sort of the so you can see with the vertical dash lines when the lockdowns occurred, they're followed by an anomalous decline in the column CO2 concentrations. And the blue line is simply showing sort of a way to disentangle the meteorological effects that may have confounded how we interpret the column CO2 anomalies. So there were many other studies that have come out since then, looking at different aspects of the Earth system. We looked at a study in the southeastern U.S. where about 80% of the fires are intentional, so they're prescribed fires that are used to maintain ecological integrity. And we saw about a 50% reduction in active fires. There are studies that have used seismic gauges to show that there is a global quieting. So just through the reduction of transportation, both through cars and trucks and aircraft, that this was detectable through these seismic networks. At AGU, this past AGU, there's even been suggestions that there was a decline in lightning activity. So this sort of these two vertical red bars indicate what they think is an anomalous decline in lightning for this time of year compared to 2019 and 2018, which they think is due to changes in the aerosol composition of the atmosphere. And then there's been studies over parts of India showing that there were improvements in water quality. So across sort of all the components of the Earth system, we were seeing these indirect impacts of COVID-19. So many of these studies can be looked at in a bit more detail through a joint NASA, ESA, JAXA COVID-19 dashboard. So the URL is here, and I think we'll be posting the slides later today or tomorrow so that you can get these links. So one of the, right, just checking my time. So one of the interesting thing that we noticed in 2020 was that despite the decrease in CO2 emissions related to changes in economic activity, we did not see a decrease in atmospheric CO2 concentrations. And so in 2020, CO2 concentrations increased by about 2.4 ppm. So here's the famous Keeling curve for Mauna Loa, and the bottom is just the bar chart showing the atmospheric growth rates of CO2 globally. And so the last column here represents the growth rate of CO2 for 2020. And what's interesting is that both it's an increase, but it's also sort of one of the largest increases of atmospheric CO2 for a non-El Nino year. So many of these sort of anomalous growth rates are taking place during 98, 2005, 98, 2005, and 2016, when there were fairly strong El Nino events. And so 2020 was sort of La Nina conditions, fairly neutral, and so it's surprising still that we would see such a large growth rate. Similarly for methane, we actually see the largest ever observed increase in the atmospheric growth rate for methane, so about 15 parts per billion. And then also the same for the third sort of leading greenhouse gas, nitrous oxide, where we saw the largest ever observed increase in N2O observations. And so for me, it's sort of a mix of surprise, especially for methane, to see the growth rate so large, but then also to some extent expected, given the role that the biosphere plays in regulating these gases into annual timescales. And so what we're seeing here is a lot of interannual variability emerging from mainly terrestrial ecosystems and how they exchange CO2 with the atmosphere. And so in 2020, this was the second warmest year on record. And the figure on the left shows the annual surface air temperatures and the departure from the 1981 to 2010 base period. And you can see over Siberia that there's this extreme sort of warming. And if you remember, 2020 was also a year of extreme fires. It began with the fires in Western Australia in December of 2019 and carrying into January of 2020. These fires, so the anomalous sort of increases in fires then were detected over parts of California and the western U.S. There were large fires in the Paraná River Basin in South America and the Pantanal, and there were also large fires over Siberia and parts of Russia. So the point here is that the biosphere was presumably stressed by these heat waves and by these low precipitation events. Some of these anomalous biospheric responses we know were due to things like the Indian Ocean dipole, so synoptic scale climatic events that were driving these climate extremes. but there really are sort of no studies to date that have looked into detail onto what the biosphere was responding to in 2020. For methane, there's several hypotheses on why the growth rate of atmospheric methane was so large. I've already mentioned that there was a decrease in NOx coming from reduced economic activity. NOx indirectly reduces the hydroxyl concentrations in the atmosphere through atmospheric chemistry with ozone. And so if you have reduced NOx, which is what we observed, you would also expect to have reduced hydroxyl or OH concentrations in the atmosphere. And so, so sort of some work has been published suggesting that if you had a 3% decrease in OH, this would actually explain the large atmospheric increase of methane that we observed in 2020. But what appears to be happening in 2021 is that we're headed for another year of large increases in methane concentrations. And so it's sort of interesting to think about how likely this decrease in atmospheric OH would be, given having multiple years of increasing or large increases in atmospheric methane concentrations. So, oh, sorry. Okay, so there's sort of a very rich set of publications and analyses that have been done to better understand these monitoring systems, the relationship of society with a variety of Earth system processes, and I think we've learned that we do have the monitoring systems to some extent, the modeling approaches to be able to carry out the attribution studies that are needed to understand the feedbacks between these different components. And so now I just wanted to move on to sort of think about how we can leverage and what we've learned through COVID-19 to incorporate that understanding into some of the monitoring and research networks that we currently have to enable our understanding of the Earth system. So here I'll put this in the context of the Paris Agreement and the recent COP26, where we're now seeing this transition from rule making. So what are the guidelines for mitigation, adaptation, and finance, to the actual implementation of the Paris Agreement. So how do we get toward the goals of the Paris Agreement to maintain temperature change below 1.5 or below 2 degrees Celsius? And so we're moving from rule making to implementation. And we have something called the global stocktake, which will be a global aggregate view of emission reductions and mitigation that will take place in 2023. And the stocktake will involve a variety of data sets that will be contributed either through the national greenhouse gas inventories or through other independent activities that the science or the policy community can carry out. Sort of going back to the summary report for policymakers, this table here is taken again from that publication over the summer, where it shows how we can link the transient response to cumulative emissions, where we can predict the expected temperature change based on cumulative CO2 emissions, where today, again, we've emitted about 2,400 billion tons of CO2, and this has driven about a 1.1 degrees Celsius warming, to the remaining carbon budget. And so we can fairly robustly understand how much CO2 can be continued to be emitted before we pass the thresholds of 1.5 or 2 degrees Celsius. And so you can take these numbers in the middle column. If we want to have a 50% chance of remaining below 1.5 degrees Celsius warming, then our remaining carbon budget is 500 billion metric tons. And we're currently emitting at a rate of about 40 billion metric tons per year. So this means we have roughly 10 to 12 years of emissions remaining to stay below 1.5 degrees warming. So in the context of what we've learned through COVID-19, where we see decreases in emissions of about 5.5%, but increases in atmospheric CO2 concentrations, we need to be able to sort of link this to how we attribute the interannual variability of the biosphere and the ocean with potential climate carbon feedbacks that might have a longer term signature. So this is another argument for sort of why these research networks are so important at the moment, particularly emerging from the Paris Agreement and COP26. We've also seen this need for lower latency updates. Often, a lot of the studies that we carry out in the science community take several years to perform. And so, for example, when we look at the global methane budget and try to understand the very interesting dynamics of methane growth in the atmosphere, these studies take years to carry out. And so there's often a lag between the scientific understanding of the connection between emissions and concentrations that needs to be resolved to more quickly inform policy, because if concentrations are increasing at a more rapid rate due to climate feedbacks on the carbon cycle, this needs to be taken into account in the mitigation strategies. There's clearly continued need to quantify uncertainties. This is fairly obvious. There's a need for sustained and open observations. Sustained being a good example with the greenhouse gas satellites. Many of the satellites are not operational. They're designed for research applications, and so there's a need to sort of sustain these instruments that have been designed for research to make them operational. And there's a need also for open observations, and so NASA has an open science data policy. So all of the data that NASA makes and creates have an open science mandate. And so it's interesting to consider how the emerging commercial sector will be making their own space observations, public or on demand in the future. These networks clearly have a role to play for early career engagement, and then also in terms of how do we coordinate these networks across regions to strengthen them and more easily exchange information. So I just have a few examples of these networks, and then we can move to questions of discussion. As I mentioned earlier, iLEAPS is a global research project within the Future Earth program. And Future Earth is a fairly new organization that has sort of built its mandate off of these 4 key programs. So the World Climate Research Program, the IGBP, which was phased out in 2015, Diversitas, and the IHDP, the International Human Dimensions Program. And from my perspective, sort of one of the main features that identifies Future Earth is this tight coupling between the human dimensions of the Earth system and the physical components of the Earth system. Within Future Earth, there are these global research projects. So here we just put iLEAPS at the center to help us understand how iLEAPS engages with the other research projects. And so you can see sort of our focus on the land ecosystem atmosphere processes and how humans are affecting these with some of the modeling activities that the AIMS focuses on, the budgeting work that the Global Carbon Project enables, IGAC, and some of the databases like Gaia and so on that they enable. And thinking about this in terms of the linkages and the synergies of these GRPs that contribute to part of the mandate for Future Earth. So it's sort of moving from global networks to regional networks. This is a figure that we've developed recently for the United States, sort of showing this wealth of investment that's been made over the past 2 or 3 decades in the U.S. At the agency level, so NASA, the Environmental Protection Agency, NOAA, that then are supporting their own research and monitoring programs to understand greenhouse gas emissions and greenhouse gas concentrations. So there are things like the missions that I've already mentioned that NASA is supporting, and for some of these that do become operational, handed over to agencies like NOAA for JPSS or to the USGS in the case of Landsat. And then there are also these field networks, and NEON is sort of, and Ameriflux are two of, I think, the most well-known of those field programs. Also within the US, at NASA, we've recently been discussing this concept of an Earth System Observatory. And the Earth System Observatory would represent a new era of integrated observations and modeling to understand the Earth system, where sort of the core missions are these acronyms around the outer circle. And the one, again, that I'm most heavily involved with is the Surface Biology and Geology mission, which will be making hyperspectral observations of the land surface and the near coastal zone. There'll also be a thermal imager measuring land surface temperature and emissivities, as well as trace gases, mainly sulfur dioxide related to volcanic activity. Other missions in the ESO are CCP, so this would be an atmospheric LiDAR measuring aerosols and cloud condensation nuclei. There will be a mass change mission, which will be similar to the GRACE gravitational anomaly mission, and then a interferometric SAR mission measuring sort of surface geologic and to some extent vegetation structure information. Beyond the US, but also sort of at the continental scale with the Copernicus program, which represents sort of a very thorough integration of observations, modeling, and engagement with the policy stakeholders and practitioners. Copernicus provides information for natural hazards, including fire, landslides, but also is now developing capacity to sort of have atmospheric trace gases included as part of their operational mandate. And so coming back to iLEAPS, iLEAPS has facilitated these networks across career stage, across geographic region, and across scientific disciplines, so that we can better understand these connections between the land surface and the atmosphere. We have an open science conference planned for the spring of 2023. It's been postponed now for a couple of years due to the ongoing pandemic. And so we're really hoping that February 2023 or thereabouts will be the date of this conference. But this is building off of 5 previous open science conferences that have enabled connections to be made between scientists, and have led to several workshops that have had outcomes such as publications on air quality and ecosystem interactions led by early career researchers. This is a figure taken from the COCO2 team in Europe, who are developing some of these prototype schemes that feed into the Copernicus program. And I wanted to show this as sort of an example of how we can think about engaging across these networks at different spatial scales and across different temporal scales to understand the processes and feedbacks of the Earth system. And so at the local scale, we can think about individual power stations. So we think about individual cities and the information that we can retrieve from those local scale studies, and then move these up to global scale studies where we're using the in situ or the FLASK or the satellite networks to measure greenhouse gas concentration changes in the atmosphere from year to year. And then we can think about sort of who the stakeholders are in terms of policymakers, all the way to land managers that may be carrying out these mitigation and adaptation strategies. So, so my last slide. So hopefully, I've sort of shown that just despite and sort of amidst this tremendous social upheaval that the COVID-19 pandemic has resulted in, it's also given us an opportunity to explore how well we do currently understand society and its role within the Earth system. The second theme that hopefully I've shown is sort of that the implementation of the climate mitigation activities we have on hand requires sustained monitoring, but also we need to understand the mechanisms that are driving atmospheric trace gas concentration changes. And so even though we saw these decreases in CO2 emissions in 2020, these were associated with quite significant increases in atmospheric CO2 concentrations. And I think we have a general sense of why, but it needs to be more precise in terms of how we do that attribution. And that these research networks play a tremendous role across different scales, from global scales, things like Future Earth and the role Future Earth plays, to the national and continental scale networks like Copernicus, to the groups like iLEAPS and the workshops or the Open Science Conference that we have to help people and facilitate the discussions on sustained observations and to provide these opportunities to early career scientists. So with that, I think we have time. We have about 10 minutes for questions, discussion, clarifications.
Thank you. Thank you very much, Ben, for such an exciting talk, actually. And it was really interesting to see how the world has changed after COVID with the atmospheric composition and all. But unfortunately, we cannot wait for a pandemic every time to make any change. So let's hope and let's work together towards a better future, actually. And when I look into the chat box, there is one question from Saurabh Sonwani from University of Delhi. I'll read it for you, Ben. As you have mentioned that there was a significant reduction in CO2 and NOx was mentioned in COVID-19, maybe due to the less anthropogenic emission during lockdowns. Is there any observation related to the VOC for same period, as both the species may be also related with VOC chemistry? Any comment? That's his question number one. And he has one more question. Is there any decline noticed for global atmospheric temperature with decreasing CO2 concentration during COVID-19 period? Is there any opportunity in the Earth System Observatory for ECRs working in the field of atmospheric science?
So on the first one, I can speculate a little bit. It's a little bit outside my area of expertise. What I do know is that there are interesting sort of inferences you can make about NOx and CO2 emissions, where you can use NOx with its shorter lifetime as a way to potentially pinpoint where that the combustion activities are taking place, and then use this to sort of disaggregate and better understand where the CO2 emissions are coming from. I'm not aware of any studies that have looked at NOx and CO2 in the context of COVID-19. So this could be an area to look at. In terms of the VOC chemistry, I'm not sure, and I would defer to somebody who knows more about VOC chemistry than myself. On the second question, well, we know that 2020 was I think tied for the second warmest year on record, and we didn't see any decrease in greenhouse gas concentrations, and so we wouldn't expect to see a cooling. The news this morning coming from the Copernicus program is saying that 2021 was the 5th warmest year on record, and again, based on I think some of the projections that Global Carbon Project has made for the CO2 concentration growth in 2021, and what we're seeing from NOAA for methane for 2021, we're also seeing large increases in those greenhouse gases, and so that's sort of consistent with the warming that we're also seeing for 2021, and that we're hearing about in some of the news this morning. So. And then the last part on the early career involvement, I'm not sure if that was a question or, but yes, I think you can see that there's lots of room for any sort of involvement in trying to answer these questions, and that a lot of them still remain unresolved.
Okay, thank you. I don't see any other questions in the chat box. So if there are no more questions, maybe we can conclude the session, Pallavi.
Samina, I have one question to Ben.
Okay.
Thank you very much, Ben, for the enthralling talk. I have one question, that is short lockdowns like in COVID can be a solution for climate change mitigation? Can you comment on this, please?
I think that's a really good question. The answer is no. And I think this is, I think it's very worth to consider that. I think some of the studies that were done to look at sort of the Earth system response to these lockdowns have the potential to be misinterpreted as mitigation strategies. And so we've been careful in the ones that I've been involved with to make sure that we're saying that this is not a direct experiment of how to mitigate greenhouse gases, and that this is sort of the worst case scenario for how we're understanding society and the economy and how this relates to emissions. So in short answer is no. But it has sort of as we've seen, we've learned a lot. One thing I didn't mention is that it also has sort of highlighted the challenge that we have to reduce fossil emissions by half in the year 2030 to avoid 1.5 and to some extent 2 degrees warming, because we would need to have sustained decreases in fossil emissions like what we saw in 2020 for the next 8 years. And we've already seen this rebound to 2019 emissions in 2021. And this is sort of eating into that remaining carbon budget even further. So I think that is one of the messages that has come from this, that sort of the discomfort and that the lockdowns have created, and sort of the minimal impact that it's had on sustained reductions in emissions, really highlights the need for us to be more serious about how we can reduce greenhouse gas emissions over the next decade, and sort of to 2050, where hopefully we're at net zero.
Thank you so much. So now we come to the end of this session, and before I officially declare the session to be closed, on behalf of the organizing committee, I would like to pay sincere thanks to Ben for his enthralling talk and vivid description. So he talks about the following points, that he provides about the description of Earth fleet, including JPSS, ISS instruments and mission. He also explains about the Industrial Revolution, the CO2 emission and temperature rise, the interrelationship of COVID-19 lockdown and Earth system response, particularly with NOx CO2 variability, and 50% reduction in active time was observed in Southeast USA, and GHG concentration increased by record if we are taken with respect to CH4 and nitrous oxide, and also mention about the future Earth perspectives, iLEAPS and GRPs. So I like to thank to Ben for taking his time out from his busy schedule and accept our invitation for delivering this talk. I'd also like to thank to the attendees who took active participation. And last but not the least, iLEAPS, UKCEH, and Samina for their help and support in successful completion of this first talk of the series. Thank you very much.
All right, thank you so much. Yeah, and thank you everyone for joining. Feel free to reach out to me directly if you have questions.
Okay, so thank you all for participating. And with this, we are just closing the seminar. Okay, thank you. Bye.
Thank you. Bye.
Bye.